Hi, welcome to today's lesson. We're going to be talking a little bit more about polymers. Yesterday you will have practiced naming and drawing the polymers and going backwards and naming and drawing monomers. And what today we're going to be looking at is how they can be arranged and how that affects their properties. Now, first of all, your retrieval task, I want you to do some more practice in drawing the displayed formula of different esters because it is a toughie. So the more you practice, the better you will get. Now remember the ethyl bit you draw second comes from the alcohol, and the propanoate bit comes from the carboxylic acid. So ethyl meaning it's got 2 carbon atoms, prop from propanoate means that it has got 3 carbon atoms. Again, underneath, methyl meaning 1 carbon, ethanoate, F meaning 2. So even if you need to go back and look at your notes from yesterday or even from last week, do have a go at practicing how you can draw out those structures. Pause the video, and when you're ready to go through the answers and when you've practiced them, just press play. So let's have a little look then. So ethyl is the second bit on the end. So you've got your ethyl group, which is your CH2 followed by your CH3, so your 2 carbon atoms and then 5 hydrogens, and that's attached to propanoate, which means 3 carbon atoms, so 3 carbon atoms in a row. On that final carbon atom you've got your C double bond O and the other O joining onto the ethyl at the end. So methyl ethanoate, so instead of having an ethyl group on the end of 2 carbon atoms, you're going to have 1 carbon atom with its hydrogens, and then ethanoate means 2 carbon atoms, the final one with the C double bond O and O coming off it. So you can see there that you have 2 carbon atoms and then 1 for the methyl bit. Now, like I said, it's tricky. If you are struggling, we'll do some more practice, and it's just keep practicing each time. But go back and watch the video from last week on carboxylic acids and making esters if you are struggling. So like I said, for today's lesson, we're going to be talking about polymers in a little bit more detail. Now, hopefully you're confident in how you name them and how to draw the shorthand version of them and gain all those 3 marks in an exam question. So what we're going to do today is look at the different types and describe and explain the different properties of each different type. And then we're going to finally bring it back to the environmental side of it and look at the disposal of just plastics in general. So hopefully you've already got some prior knowledge of that, but it will come in really handy and it's quite relevant to our lives as well. So firstly, what I want you to do is I want you to look at these polymers. So these are examples of synthetic polymers. Synthetic means that they are man-made. There are naturally occurring polymers, and we are going to talk about that next lesson. So these are man-made polymers. So it shows different polymers and how they are being used. Now what I want you to do is I want you to categorise the polymers used for these uses into 2 groups. And I want you to justify why you've grouped them in that way. I will show you how I've grouped them in a little while, but I want you to think about the properties and how you might group them together. So the one that you might not be able to tell what it is a car engine cover. It's not the engine itself, it's a cover. So if you lift up the bonnet of a car, you would see on some cars they have a cover made of plastic but covering the engine. So pause the video, put those into 2 groups and then explain why you've done it in that way. Okay, so the way I've done it is that I've got the plastic bag, the plastic cup and the polystyrene cup, and then I've got the engine cover, the hairdryer, the spatula, the microwave pan and the Xbox. So we've got our 2 different groups there. And the reason I've grouped them in this way is because the 3 on the left hand side, so the bag and the 2 different types of cups, will melt. And the ones on the other side do not melt. So they are more capable of withstanding high temperatures. Obviously, inside a car engine, it gets really hot, so the engine cover needs to be sure that it doesn't melt. The hairdryer is designed to get hot, just like the spatula and the pan that goes inside a microwave. And obviously, we might know that Xboxes had a problem of getting really hot and therefore breaking down because they were really hot, but not at any point did the plastic melt. Now, the reason that these two groups have different properties and that some will melt and that some won't is that they're made from different types of polymers. So if we look at these ones first, these are what we call thermal softening ones. And as we know, a polymer is made up of chains, long chains of alkanes, basically, because you've joined your alkenes together, breaking that double bond, and the monomers just join on and on and on and on. Now, inside that plastic, you wouldn't just have one long chain. You would have many, many, many long chains, sort of all intermingled, and you can see it in the diagram. Now, not at any point are those chains joined to each other. They're just all mixed together, but not attached, which means that they're more easily separated. Now, if we look at these, you can see that the chains are actually joined together, which means it's a lot harder to break those chains apart and therefore cause them to melt. And these are called thermosetting polymers. So we've got thermosoftening and thermosetting. Now, what I want you to do is I want you to think now, look at these diagrams. These are very, very, very simplified versions of the other diagrams. And sometimes you just see each polymer drawn in this way. So they're just drawn like long threads to represent the polymer chains. Some are attached, some aren't. So what I want you to do is I want you to copy the diagrams and I want you to name which type is which and then give an example of something else that we've not talked about that might be made out of each of these polymers. So pause the video and stop it when you're ready to go through it. So hopefully you've got that the first one is a thermosoftening plastic. So it will melt. They're not joined together. They're not bonded. The chains are not bonded together. They're just intermingled. And if you tried to separate them, it would be very easy. And the second, it looks a bit like a brick wall because you have cross links between the chains which join them together, which means they are thermosetting and they are more fixed in position and they're not easily separated. So thermosoftening, we said plastic bags, cups, polystyrene cups. Sometimes if you've ever noticed, for example, if you've ever had like chips or something from the chip shop or from a takeaway and they've come in a polystyrene tray, if they're really, really hot, you will notice that it does start to melt at the bottom. They don't melt as low as, say, a plastic bag would, but they are still low melting point. Whereas thermosetting, obviously, if you're going to use a spatula for cooking, you need it to have a high melting point. So let's think more about thermosoftening then. So we've already said plastic cups, plastic bags. Other examples you may have come up with are, I came up with children's balls out of a ball pond or straws, anything like that that we know would melt at a low temperature. Food packaging, unless it's designed to go in the microwave, would be another example. So plastic bottles is a classic example. Now thermosetting, it has to be another example of something that's maybe designed to withstand high temperatures and wouldn't melt easily. So I came up with sort of crockery. This is melamine, it's called, and it's designed to withstand high temperatures, or the interior of, let's say, a car dashboard that's still near the engine. It has wiring behind it that could get hot. So anything that's attached to electrical equipment, so plugs, for example, if the wiring goes wrong, it might get hot and it still wouldn't melt. So now we've identified our different types of polymers, what we need to understand is why they are different and be able to link the structure to their properties. So all plastics have some general properties that they share. So whether they're thermosetting, thermosoftening, they all share general properties. They don't conduct electricity and they're really poor conductors of heat. So you wouldn't use them in something that you want to transmit electricity or heat through. Metals are a much better product for that. They're unreactive. So most of them you can't, they're not affected by air or water, and a lot aren't affected by chemicals. Some are, but generally they're not. So that's why they're really useful in food packaging and just packaging in general, that you can put anything inside of them and they're unlikely to react. They're going to last a lot longer. Now, this can be both good and bad. So it means they're more durable and you can handle, or you can store products that may be quite dangerous, but it means that they're really difficult to dispose on. That's something we're going to talk about later. And if you look at that top picture, you've got a baby's teething ring. Obviously, that's important that one, it's unreactive, and two, that it's really durable. So if a child is chewing on it, put it in the mouth, it's not going to cause any harms, or wear by it and then get bits that are going to break off and harm the baby. So, like I said before, all the properties of plastics depend on how the chains are held together. Now, before we start talking about thermosetting and thermosoftening plastics in contrast to each other, I want us to think a little bit more about thermosoftening plastics, because they can fall under two categories as well. And we're going to look specifically at polythene. So the proper scientific word is polyethylene. Sometimes you might see it called polyethylene, and obviously we shorten it, it's a polythene bag, but it's made from polyethylene. Now, thermosoftening plastics can be what we call branching chains or lined up chains. So, for example, low density polyethylene or polythene that's used in plastic bags is branching chains. So it makes them soft and light and easy to melt. So if you look, the chains in that diagram aren't close together because they're branching, the chains can't get very close together. That means they're even more easily to separate. Now, lined up chains, so they've got no branches coming off them and the chains are a lot closer together, make the plastic a little bit more dense, a bit more rigid, and slightly harder to melt. Now, all of these are still thermosoftening. The chains are not touching, and they're not attached to each other. They might touch, they might intermingle, but they're not attached in any way. So they're still thermosoftening, they're still easily separated, so the melting points are relatively low, but the lined up chains are slightly higher. The reason for this is that if you look at the diagrams at the bottom, the first one on the left is the low density polyethylene, or the one with the even lower melting points, and that's because the chains are further apart due to the branches, they've got what we call weak forces of attraction. So they're further apart, and that means that it's much more easy to overcome those forces of attraction. You don't need a lot of energy, so that if you tried to melt a plastic bag, you really wouldn't have much difficulty at all. They melt at very low temperatures because the chains are far apart because of the branches, so they separate with a very low amount of energy. Now, on the right, you've got the higher density polyethylene. And as you can see, there's no branches, lined up chains, which are then closer together. So because they're closer together, they got stronger forces of attraction, which means you need more energy to overcome that attraction to get them to break apart. The chains still aren't attached to each other, so they're not thermosetting, so they do still melt at relatively low temperatures, but you just have to heat them up slightly more than a branched chain. So they would be used for things like plastic bottles, pipes and buckets, things that might get warm but aren't really designed to withstand really high temperatures. So the low density ones are used for things like carrier bags, bubble wrap, anything that would melt at very low temperatures. So thermosoftening plastics, we'll continue to talk about them, they melt when they're heated. Most plastics that we come across are thermosoftening, so things that you might automatically associate with being plastic like cups and bottles and plastic knives and forks, say if you're at a picnic or something like that. All those are thermal softening, but so they melt and they're not very durable. But it does mean that they can be recycled, because when you recycle a plastic, you've got to melt it and turn it into something new. Now, the thermal softening plastics don't have covalent bonds between the other chains. We've talked about that. On the right, you can see 3 different ways of drawing these out. You might see these at different times, but in none of these examples could you see that they're actually attached. The chains are just mixed together or they're lined up, but they are not attached together. They've got no cross links. If you look at that bottom sentence, thermal softening plastics have no cross links between the polymer molecules. So when you heat them up, when you heat any particles up, they move more. So basically the chains, when you heat them up, they're free to move, and they slide over each other, and that's what they move apart, and that's what causes it to melt. So the key thing is no cross links between the polymer chains. They're not bonded together. So they can slide over each other and they have low melting points. Now, if we compare that then to a thermosetting plastic, so we said hair dryers, kitchen utensils, anything that's designed to withstand a high temperature, they've got cross links between the chains. So you can see on that first diagram, you've got the chains and you've got those bonds in between them. So they do not melt. If you were to heat them up or try and melt them, they might burn or they might char at extreme temperatures, but they won't melt. They are much more resistant to high temperatures. So they're used to make things like plugs and anything that is likely to get hot and then could cause problems if it did melt. So obviously if you've got an electrical appliance, the plastic is used because it's not an electrical conductor, so it keeps us safe. Now if it was to melt, if the appliance overheated, then you'd have electricity that was able to not be contained within the appliance and potentially cause harm to the human using it. So the key point is that the covalent bonds in a thermostatic plastic are strong. So they have cross links with strong bonds. And this means that even when you heat up the plastic and try and melt it, those cross links with really, really strong bonds, you don't overcome that bond enough to break them apart. And that's what gives it the properties of being of having very high melting points and being a lot stiffer. So what I want you to do now is I want you to construct this table. Now you might need to write a sentence rather than just one word in the box. And I want you to come up with key features. So if you're going to say one will melt, then in the other column you would put the other one won't melt. You need to talk about the structure, you need to talk about cross links or anything like that. So you might need a little bit more space than just one line for each. But I want you to think about the key properties as a comparison between the two. You might want to draw a diagram as well underneath. So pause the video, and when you're ready, press play and we'll go through some answers. Okay, so thermal softening have low melting points. So that means that thermosetting have very high melting points. So as you can see, we're doing a comparison. So whatever you've said for one, you need to write the opposite for the other one. So thermal softening, no cross links between the chains. So if you've not got these, make sure you're using a different colour pen and adding them to the end because they're very, very important. So thermosetting, cross links between the chains. Thermal softening used in packaging and pipes. Thermosetting using kitchen utensils and car parts. You can also put electrical appliances or anything else that you can think of that would need to withstand high temperatures. Thermal softening has no covalent bonds joining the chains, whereas thermosetting has strong covalent bonds joining the chains. Thermal softening can be recycled easily because they melt and you can melt them down, mix them together and turn them into something else by letting them harden. Thermosetting cannot be recycled easily because they don't melt very easily. And finally, The chains can move over each other, so this is why they're generally flexible. If you think about a plastic bottle or a plastic bag, they've got a lot of flexibility, bubble wrap as well, cling film, things like that. Whereas thermosetting, they're a lot more rigid because the chains are not free to move. They are bonded and they're stuck in one position. So make sure you've got all those key points down. I hope that you've got at least sort of 3 or 4 in each column, and especially about the cross links, the strength of bonds, and the melting points. That's really, really important. So finally then, and this is something that I'm hoping you've got a little bit of understanding of already, so you shouldn't find it too difficult, we're going to think about the disposal of plastics, and we're going to need to compare the different properties, the different ways of disposing them and how it links to the properties and how it can then lead to an environmental impact. So what I want you to think about now is there are 3 methods of disposing of polymers, and I want you to look at these pictures and tell me what you think those 3 different methods are. So pause the video, write those down, and then you can start when you're ready to go through the answers. Okay, so first one, hopefully you've got that's recycling. Now the middle one, you've got a fire. So it's incineration, which basically means you burn the plastic down. And the last one, hopefully you can see that big pile of rubbish, is landfill. So these are the 3 ways that when you put your rubbish in the bin at home or at school, this is what your plastic would undergo. So we're going to talk about each one in a little bit, and you're going to need to be able to evaluate the advantages and disadvantages of it. It might be worth making notes. I'm just going to talk about them, and then you need to be able to pick out what's an advantage, what's a disadvantage, because you're going to do a little bit of writing for the final task. So, landfill. Now, this is any recyclable plastic, or well, I suppose if people don't recycle, it's any plastic. But plastics are non-biodegradable, which basically means they're not broken down by microorganisms. So if you just leave them on the ground or in the ground, they don't disappear, they don't break down, they don't decay, they don't go anywhere. So some plastics can last thousands of years, and they just, when you stuff them under the earth, and they would stay there. Now, as a result of growing population and the amount of packaging that we use, landfill sites are difficult to find, and they are becoming full. So we're running out of space to put plastics and any rubbish, really, because the things that we're putting under the earth aren't biodegrading and wasting away. We can't then add more to it. It's just full, and we need to go and find somewhere else to put it. Now, not only are the landfills filling up, but if you put plastics into landfill, they can leach chemicals into the ground, and other products can do it as well. But any landfill site will start to have toxic chemicals leached into the ground, which then obviously can run off and get into drinking water, could harm plants and animals, and even harm us. Now, landfill's not all bad, because it does prevent the need for incineration. So if you've got a plastic can't be recycled, it's either going to go to landfill or it's going to be incinerated, which you'll find out in a minute causes its own issues. So it does give a good solution to the problem of disposing of plastics that are not recyclable. So moving on to recycling then, obviously we are really promoted to recycle. It is the best option when possible. So it prevents the use of landfill and incineration, and basically means instead of making new plastics and using more crude oil, because that's where plastic inevitably comes from, you're using valuable resources again and again rather than making new stuff. So like I said, crude oil is a finite resource, so we don't want to use it over and over. We don't want to use more than we need to. So recycling also reduces the problems of the disposal. So you don't have to use a landfill and you don't have to incinerate it. However, you do have to melt it and turn it into a new polymer. So you probably know yourself that if you melt something, you can melt plastic and then it will harden again. And that's exactly what happens with recycling. However, when you put things in a recycle bin and it goes off to wherever it goes, it's got to be separated into the different types of plastic, because if you were to try and melt it as a mixture, the resulting plastic would not be as strong or as durable. You're compromising on the properties of that plastic, which might make it not as useful. And then obviously it's time consuming to separate it, which can lead to expense. Now, like I said, when you recycle, you've got to melt it down, which then obviously means you've got to heat it up, and that uses energy. Now, we've said before, anytime we're using energy, generally it's coming from burning fossil fuels, which then releases pollution, leading to the greenhouse effect and global warming. So recycling still has some impact on the environment. And obviously, recycling is brilliant and we should be encouraged to do it, and we should do it as much as possible because it is definitely a better choice. But not all plastics can be recycled. So sometimes you need to separate out the ones that you can't recycle, or they just have to go to landfill or incineration. So this is where we lead on to finally. So this is for the non-recyclable plastic. So the other alternative is that you put it in landfill, but not always the best idea. So they incinerate it, and basically it's put in a big furnace and it's burnt. So it's set on fire at very, very high temperatures. Now, you might think, oh, this is terrible, and it's not the greatest, but there are some good things about this as well, in that it releases a lot of energy. So that energy can be used to generate electricity or heat homes, or in turn to heat other things up. So you can harness that energy and make use from it. So it's not all bad. However, it is bad in that carbon dioxide is produced, which is a greenhouse gas contributing to global warming. And you may know that when you try and burn a plastic, toxic gases are released, which must then be removed before leaving the chimney because it can harm health of humans and animals and pollute the air. So toxic gases, obviously a bad thing. But incineration does prevent landfills from being used, so you've not got the problem of needing to find more space under the ground. So good and bad things about each one of those disposal methods. So what I want you to do now, we're going to kind of practice an exam style question, which would be worth 6 marks, where you've got to evaluate. So that's a really key command word, evaluate the different methods. Now, when you evaluate, you must compare the advantages and disadvantages of each one. Now, remember, you can't just list. You can't just say, this is a disadvantage is that it gives off carbon dioxide. You would need to say why that is a bad thing. You've got to elaborate on these rather than just listing a load of features. So there's your criteria. Okay, so you've got to compare the advantages and disadvantages of each method. I would go for at least 2 of each. Give your opinion on which one you think is best with a justification. That bit you can't be wrong. Your opinion is your opinion, but you've got to back it up with a justification. And make sure you form your answer in paragraphs with good use of grammar and punctuation, and spell all the scientific terminology correctly. So I would advise that you do a little separate paragraph for each of the methods, and then once you're done and you've written your conclusion, I'm going to give you the answers and you can assess your work. So pause the video now and start it again when you're ready to go through the answers. Okay, so let's see how you got on then. Obviously, people in class would be doing this with a printed mark scheme, and you would be peer assessing this and getting feedback. But what I've done at the bottom is I've put a table of some of the advantages and disadvantages that you may have put in your answer. Obviously, you would need to elaborate on them more than I have, but I've just split it up to the things that you might want to include in your answers. So what I want you to do now is I just want you to imagine that you've got that mark scheme in your book, and that you are circling which bit you have done. So did you compare the advantages and disadvantages of recycling? And what I would say is you need to get, yes, you must include at least 2 bullet points from each side with a little bit of an elaboration. So don't just say no landfill. Why is that a good thing? Okay, saves resources. Why is that a good thing? So because you really need to expand on your answers to get that level 3 mark. If you've not expanded on it, you've just kind of listed it, but you've done everything else, you'd be looking at a grade like a level 3, a level 2 answer, which would be 3 to 4 marks. And if you just kind of put not a lot and your answer just kind of is lacking detail, and you've maybe only put like one advantage for one thing and a disadvantage for another, you could possibly still gain 1 or 2 marks for that. So go through your answer. You might want to use a highlighter and highlight the key points that you have made that are in that table at the bottom, and set yourself a target underneath. So it might be that you've not talked about something that's really crucial, or you've not elaborated on why something is an advantage or a disadvantage, and then set yourself a target on how to improve your answer, because this is the kind of thing that you might be asked for in your 6 mark question. So that's it for today. Any problems, do send me an email. If you want me to look at your answer, that's fine. Take a picture and email it to me. I'll be happy to go over it for you and give you some feedback if you're struggling. But great work, and we will see you tomorrow for our final lesson of new learning for the week.